Hello, I'm Konstantin, and I'm going to talk about universally robust information aggregation for binary decisions. This is joint work with Itai Arieli, Yakov Babichenko, and in Vital Cohen. In many real-life situations, before taking a decision, we have to merge information obtained from several sources. For example, before deciding whether to pick an umbrella or not, we may want to check different weather forecasting websites. Let's demonstrate our settings through an example. Consider some decision maker, for example, a politician, who thinks about the possibility of implementing a public project. Unfortunately, the decision maker doesn't know whether the project will be beneficial or detrimental. So there is some state specifying whether the project is beneficial or not, and the decision maker only knows the prior distribution on the values of the state. To improve the decision-making process, she conducts a binary answer survey among some agents, which are just members of the public. And since we assume the decision maker is a honest public servant, we consider a common interest scenario, which means that the agents and the decision maker all share the same utility function. And because the agents are just ordinary members of the public, we assume that they are symmetric, which means that each of the agents have some private information about the state, and the information obtained by different agents is identically distributed. We further assume that the decision maker knows the distribution of the private information of each agent separately. And because the scenario is common interest, we assume that the agents are truthful, which means that an agent recommends implementing the project if and only if, according to the private distribution and her private information, she believes that the project is more likely to be beneficial than detrimental. And the catch is that the decision maker doesn't know the correlations between the private information of different agents. And these correlations are chosen by an adversary. The decision maker, therefore, aims to aggregate the information robustly well over a single iteration of the game. And what do I mean by robustness? Well, of course, there are several robustness paradigms. Arguably, the conceptually simplest paradigm is minimax, which focuses on just maximizing the decision maker's expected utility under the worst possible adversarial choice of the correlations. Alternatively, one can consider the benchmark of a hypothetical Bayesian decision maker who knows the correlations between the distribution of private information of different agents. A first approach under this benchmark is regret, which focuses on minimizing the difference of expected utilities of the Bayesian decision maker, the benchmark, and our ignorant decision maker. Alternatively, one can consider approximation ratio, which is very similar to regret, but instead of considering the difference of the utilities, it focuses on the ratio. Our first result is that in the setting with symmetric agents, it is without loss of generality that the decision maker conducts an anonymous survey, which means that the decision maker only observes the statistics of the recommendation of the agents and not the identities of the agent making specific recommendations. One well-known aggregation rule is called random dictator. Under this rule, the decision maker just picks one agent uniformly at random and follows her recommendation. And this aggregation rule is known from previous literature to be optimal under the minimax approach. Our first main result is that when the number of agents is large enough, all three robustness paradigms, minimax, regret, and approximation ratio, are equivalent. And moreover, there is just one optimal aggregation rule, which is random dictator. However, this equivalence between the three robustness paradigms fails when the number of agents is small. Our second main result is the characterization of the minimal regret for any number of agents. We proved the minimal regret is just the Jensen gap of the probability that a Bayesian decision maker guesses the state correctly, where the Jensen gap is just the maximum possible difference between the two sides in Jensen's inequality. This result is a bit surprising because it expresses the guarantees of the ignorant decision maker in terms of the utility of the Bayesian decision maker. Thank you very much for your attention.